Hey, it's Dr. J. Today we're going to talk about domain and range, section 3.2 from the textbook. We'll start with domain, and I'll do quite a few examples of domain, and we'll come back and talk about range later. So let's just briefly review what the definition of domain is. It's a set of all possible inputs, also known as X values. For a function. That's it. That's the definition of the domain, the set of all possible inputs. And I have to make a confession. In the introduction, we give you a very stripped down definition of the domain. We don't, or I didn't, typically at the beginning introductory level, it's very common to not consider every possibility. Before I do any actual problems, let me just give you the idea. In section 3.1, if you had a table of values, I'll just pick one of the problems that we did. I don't know, let's say, I don't know, let's just pick one. Let's pick absolute value of X, yeah, or maybe function notation. These are the same function either way. So I'm not going to go through all the details again. We already did this. We would say, you know, -2, you plug in the -2 in for X, and you're going to get +2. I'm not doing all the work again today. If you plug in -1, you get +1, and if you plug in 0, remember you're plugging your X's into the absolute value to get the Y's, yeah? 0 comes out 0, 1 comes out 1, and 2 comes out 2. Okay? And the primitive definition, and I'm using that word very loosely, was what I would have asked for in section 3.1. I would have just said, what's the domain? And you would have just given me all of the X values, -2, -1, 0, 1, and 2. All right. And in section 3.1, I would have accepted that as the answer. Yeah. Because in section 3.1, I hadn't given you the full story of what the domain is. The domain is technically all possible inputs. Yeah. So this answer is okay in the introduction, but not actually correct according to the definition. According to the definition, I have to consider all possible inputs, right? If this was actually correct, and this is what the graph would look like, it would look like 5 dots. And this is what I did in 3.1. All right. If these were the only possible, then the dots would not be connected. Going to say dots are not connected. If these are the only possibilities, yeah, but they aren't, okay? This is a primitive domain, or what's called a subset of the domain. It's not every possibility. There are other possibilities. For example, what if I plugged in 1/2? All right. I know I didn't, but it's possible to plug in 1/2, right? There's nothing preventing me from plugging in 1/2. So that means there should be a dot here. Yeah. So just because I didn't use it doesn't mean that it wasn't possible. So oftentimes when we make a table is primitive, right? It's a subset of all of the possibilities. So what am I getting at? In section 3.1, you can give me the primitive domain or the subset of the domain, and I won't even really use that terminology. I'll just say find the domain, because that's all you know, right? That's why we call it the primitive. It's like as if these were the only numbers that you ever knew about, right? But there are lots of other numbers, right? I could have plugged in -3. I know I didn't, but I could have, and then that would have given me a dot up here at +3. And so on and so forth, right? I could have plugged in millions and millions and millions and millions of points. So when you say all possible, that means that the dots are connected. And so as we move forward through the rest of chapter 3, we're going to be connecting the dots, and we're going to give the actual domain. All right, and so from this point forward, anything, moving forward in chapter 3, when I ask for the domain, I do not accept a list of numbers anymore. It's just not going to happen. You're going to have to tell me every single possibility. So x could have been 1, it could have been 2, it could have been 3, it could have been 4, right? I could have gone all the way to infinity. And we call this right infinity. Excuse me. You can also call it positive infinity. Some people go so far as to put a plus sign here. I could have plugged in -2. I could have plugged in -3. I could have plugged in -4. I even could have plugged in decimals and fractions and all sorts of other numbers. I could have gone all the way to negative infinity. This is what I call left infinity, or negative infinity. So the domain, the actual domain, all possibilities, is the set of all x such that x is any real number. X could have been any real number. It goes all the way to negative infinity, goes all the way to positive infinity. And so this is referred to as the set of all possibilities for x. X could have been any real number. Okay? So that is the true definition of domain, not the primitive introductory definition that we used at the beginning to sort of get the idea going. Okay. So in this lesson, we're going to be giving the domain in two possible notations. One is called set notation, and the other is called interval notation. Oh man, I lost my focus. Come back to me. Come back down. I need you to focus. There we go. So there are two basic notations. Now, let me actually give you the idea. So suppose you have a number line. We'll call this the x-axis. It's really misbehaving today, isn't it? Come on. Focus. I need you to focus. There we go. Come on. Stay focused. So suppose you have the x-axis. I'm only talking about domain right now. This will apply to the range later in the lesson, but right now I'm just focusing on domain, so I'm only going to look at the x-axis. The right-hand side is positive infinity, sorry. The left-hand side is negative infinity. And then we're assuming that the arrows go on forever. All right, and then this axis is referred to as the x-axis. Or you could just say x. Okay. If every real number is allowed, right, that means that you can include every single possible number, the whole number line. Then we have the set notation. I would say the set of all x such that x is a real number. Keep losing my focus. That's called the set notation. The interval notation is parenthesis, negative infinity, comma, infinity. This is called the interval notation. It's just two different ways of saying the same thing. Now, let's go through several different possibilities before I actually do any problems, okay? So suppose that we could not go anywhere we want on the number line. Suppose there's some restriction or some limitation on the number. All right, so let's suppose f of x was the square root of x. All right, just start with that for an example. Well, if f of x was the square root of x, remember when I made my table, I did not allow any negative numbers. All right. I mean, I think I tried a couple negative numbers, and we ended up getting imaginaries. And so in this chapter, we're not using imaginary numbers. See my previous lesson for the commentary on that. And I'm just going to review this very briefly. If you plug in 0, you get 0, square root of 0. If you plug in 1, you get 1, and the square root of 1. Be careful with the next two. You plug in 4, square root of 4 is 2. And you plug in 9, the square root of 9 is 3. Okay? And so when we drew our graph, and I'm only going to do this very quickly, it looked like this. Maybe just for this particular example, I'll stop at 4. All right. And so what is the domain now? All right. Well, the domain is all possible x's, not just the ones that we used. Yeah. This is the primitive domain, or the subset of the domain. The actual domain is every number greater than or equal to 0. And so that means in my domain, I could have used 0. I could have used any of these numbers that were greater than 0. So this is the actual domain. It is not all real numbers. It does not include the negatives. And so my set notation would be the set of all x such that x is greater than or equal to 0. So we would not include any of the negative numbers, but we would include 0. This basically means x is equal to 0 or x is greater than 0. We combine those two together and it becomes greater than or equal to. And so the interval notation for this is 0, comma, infinity. That would be the interval notation for the domain dom of this particular function, the square root function. So there are basically three possibilities. The first possibility is that it could be any real number. I'll go through some examples of that. Just sort of getting warmed up here. The second possibility is you could have something like a square root, in which it would be greater than or equal to 0, in this particular example. There is a third possibility for domain. You could have a rational, or what's called a reciprocal function. If you remember, in the reciprocal function, this was the one that had the really big table. Lots of x values for inputs. Again, you can watch the other video if you want to see the long version of this, but I'm just going to go ahead. If you plug in all of these x's and plug it in for x, you're going to get -0.5, -1, -2, DNE does not exist, 2, 1, and 1/2, and again, C3.1 for a longer explanation of that. And then what the graph look like, here's your x, here's your y. I'm not doing range right now, I'm just doing domain. And then we plotted these points just very quickly. I don't want to go through all the details. Otherwise, I'll be here for another hour and a half. But just roughly, this is roughly what your graph looked like. Okay. It's not very good, but it's rough. I know I'm not using graph paper or anything like that. But in this lesson, we can be rough with pretty much every one of these problems. So in this problem, the denominator could not be 0. Yeah, the denominator could not be 0. So when you talk about your domain, you're looking at the x-axis. Yeah. X could go to positive infinity. By the way, I'm going to get really sick of putting positive signs on infinity, so I'm just going to say infinity. That means positive infinity. But for left infinity, negative infinity, you have to put the negative sign. All right. But x cannot be 0. In other words, you can't cross this axis. All right. This is what we call an asymptote, and I'll get more into that later. So the domain would be the set of all x such that x is not equal to 0. Everybody except 0. And so the way we write that in interval notation is -infinity to 0. Parenthesis means not including. In the last example, maybe I'll make a mental note. The square bracket means including. If you're referring to the one if you're thinking about the one I just did, if I use a square bracket, it means it's actually including 0. Because the square root does actually include 0. But the reciprocal function does not include 0. It means that you cannot touch this line. All right, so you cannot touch this line right here. It's called an asymptote. So we say -infinity, 0, U stands for union, parenthesis, not including 0 again, but going all the way to positive infinity. So this would be the domain for the reciprocal or the rational function. I think the word I used last time was reciprocal. Reciprocal, rational, they're related to each other. Okay? A reciprocal is a type of ratio, so we call it rational. Okay, so that's the introduction to finding the actual domain of a function. All right. Now this might be, a lot to take in one section, so I'm going to give you a summary of what I call the domain rules. Number one, if a function does not have a square root or a variable in the denominator, which could cause it I'm saying denominator twice. I wish I would have phrased it better. 2 equals 0. Then the domain is all real numbers. That's the easiest rule. So if I give you a function and it does not have a square root and it does not have a variable in the denominator, which would cause the denominator to equal 0, then the domain is negative infinity to positive infinity. That's rule number one. Rule number two. If a function has a square root, then the domain is equal to the set of all x such that the radicand is greater than or equal to 0. The radicand is a fancy way to say the inside of the square root. That's what we call the radicand. We sometimes just abbreviate it rad. We typically rewrite this set using interval notation. All right. And rule number 3. Now, I recommend writing these rules down, and then as we go through the rest of the lesson, you can quickly refer to which rule I'm referring to. I will verbally say it, but I'm not going to write these rules down every single time I do a problem. All right. If a function has a variable in the denominator, then the domain is the set of all x such that the denominator does not equal 0. And that's why I say which could cause the denominator to equal 0. That's what I mean down here in rule number 3 when I say the denominator does not equal 0. Okay, and then again, we sometimes, not always, but we sometimes with rational functions, it's kind of a sometimes thing. With the square root functions, it's kind of an always thing, but we sometimes rewrite this set using interval notation. All right. So those are your 3 domain rules. There is a 4th rule, but we don't learn about it until chapter 6, so I'm just going to not say it today. But when we begin chapter 6, I will mention, hey, you remember the domain rules? Well, we're going to add another rule to the domain rules. Sometimes I don't even call rule number 1 a rule. These are the ones that matter. Think about what rule number 1 is saying. Rule number 1 is saying the function does not have any of these things. So really what you want to memorize is rule number 2 and 3. I mean, do I want you to know rule number 1? Of course I want you to know rule number 1, but it's not really very much of a rule. I mean, rule number 1 is basically saying the function doesn't have 2 and 3, right? So if you memorize 2 and 3, then rule number 1 is simply the absence of rules 2 and 3. Yeah. We sometimes call this a free variable. Yeah. It means that x is free to do whatever it wants to do because it doesn't have any of the things mentioned in rules 2 and 3. All right. So keep these rules in mind. We're going to be using them for the rest of this lesson and for the rest of the course, in fact. I mean, once you know these rules, you are now, it's like you're responsible for knowing these rules at this point. Okay, so let's go ahead and do an example. Find the domain using interval notation. Sometimes I just say interval. That's a short way to say interval notation. Okay, find the domain using interval notation. This function does not have a square root. It has a square, but that's not the same as a square root. So sometimes we refer to this as quadratic so that you don't confuse it with square roots. So this does not have a square root. It also doesn't have a denominator. No square root, no denominator. Free answer. The domain is all real numbers, negative infinity to infinity. Really, it's the same instructions for almost all these questions unless I say something else. All right, so. Square root of 2x minus 10. Okay, well, this has a square root. So that's rule number 2. This is what we refer to as rad. Yeah. And so you want to set the radicand greater than or equal to 0. Right. Not just x, it's the whole radicand, 2x minus 10. You can ignore the square root when you're doing this calculation. All right. Now, be careful. Sometimes when people ignore the square root, I saw this happen a lot back in chapter 1. At the beginning of the problem, there'd be a square root. You would do something ignoring the square root, and then you'd forget to go back and pick it up. We're ignoring it only temporarily. So if you got to put a pin in it so you don't forget to go back and get it, then do so. All right. So now you're going to solve this equation for x. Or we call this an inequation or an inequality. So 2x is greater than or equal to 0 plus 10, which is 10. Divide both sides by 2. Simplify that if possible. If it's not possible, then leave it alone. But in this case, it's possible. So the domain is the set of all x such that x is greater than or equal to 5. That would be the domain of this function. Read the directions. I just got the right answer, but the wrong notation. The question clearly says interval notation. So now I take this answer and I rewrite it. Including 5. So square bracket means including the 5. It could, in fact, be equal to 5. Greater than means go to right infinity, or also known as positive infinity. So this is the correct answer using interval notation. All right, let's keep on rolling. F of x is x plus 5. Is that a 5? Looks like a 6. X plus 5. X squared plus 4x minus 32. Find the domain in set notation and then rewrite it into interval notation. All right, so this doesn't have a square root, but it does have a denominator. I'll just abbreviate that denom. Or some people say den, but then it kind of looks like domain, and I don't know, whatever. Denominator. Some people will just say bottom if you want to say that, but the proper name is denominator. You can actually ignore the numerator. Yeah. Now go back and read the rule again. The rule doesn't say anything about the numerator. Well, that's the way rules and laws are. If it's not specifically mentioned in the law or in the rule, then that law or that rule does not apply to something that's not specifically demonstrated or specifically mentioned in the law. So what you're going to do is you're going to set this equation not equal to 0 and solve it. These problems should be factorable. If they're not, you probably wrote it down incorrectly. I should say probably, because there's always that off chance, 1 in a dozen, maybe 1 in 100, where it's just not factorable. But chances are, 99% chance that this is going to be factorable. So 8 and 4 was my first guess for 32. If 8 and 4 doesn't work, I still have other choices, maybe 16 and 2, or God forbid 32 and 1. Sometimes the answer is the least likely to succeed. But this happens to be right, 8 and 4. I want to make it a positive 8 and a negative 4, so that when I multiply them, I get negative 32. And when I add them, I get positive 4. Quick review of factoring. Now you're going to use your zero product rule. Remember that these are not equal to's. They are not equal to's. They are not equal to. Some people get lazy and they still write equal, and then you end up getting it wrong because it's not equal. -8 minus 8. X is not equal to -8. You don't even have to do this math. I think every single one of you is an adult. You can all add and subtract in your head, so you could have easily just done that all mentally. Yeah. Okay, and then now for set notation, I'm going to say the domain. And watch what I do. I just take this and I dress it up. I say the set of all x. I know you have to put an extra x such that. I don't know if I've made that clear. This symbol is read as such that. So the set of all x such that, and then you take this and you put it inside the set. You can rewrite this as and, I guess. You could also just put a comma. Either one is fine. You could also say or, but I'm not going to go there today. Just get it right. Get these two numbers right, and I will mark it right, okay? And make sure it says not equal. All right, that's important. All right, and then now I want to rewrite this into interval notation. So I have the answer. Let me just kind of quickly draw what this means. So here's infinity. Remember, this is your x-axis, right? So x represents the whole line. This is negative infinity. Here's 0. Here's 4. And here's -8. And we're basically saying x cannot be 4. So this is what we call a whole. Yeah. It's as if somebody deleted the number 4. 4 has been deleted. X cannot be -8. And again, it's like the number -8 has been deleted. Yeah. But X could be all possible. That's the key. It could have been any of these numbers. It could have been any of these numbers. And it could have been any of these numbers. In other words, it's like saying you can be anything you want to be, but you can't be -8, and you can't be 4. You can go all the way to infinity, you can go all the way to negative infinity, but you can't be these two numbers. And so here's the interval notation. Start on the left. Negative infinity, parenthesis. Negative infinity and positive infinity always get parentheses. All right, I'm starting on the left, though, so I'll get to this in a second. And then you can go all the way to -8. Yeah, but you can't be -8. Right? So not including -8. Union. U means union. Again, pick up at -8. Like basically the other side of -8. Right? Skip right over 0. You don't care about 0. Go all the way to 4. But not including 4. So parenthesis. Union. Pick up right on the other side of 4. Not including 4. And then go all the way to infinity. So that would be the interval notation for this domain. And now you know why that's a sometimes rule and not an always rule. Domain and set notation, domain and interval notation. I hope you all agree, I agree too, that set notation is a lot nicer for these types of problems. but I mean, I still want you to know this. Okay. Take a good look. It's about to go away. Example 4, find the domain. For this one, we'll just use interval notation. X squared plus 7 divided by 5. Square roots? No, no square roots. Yeah, there's a square, but no square roots. All right, how about denominators? Yeah, well, there's a denominator, but what do you notice about it? There's no variable. If there's no square root, there's no variable in the denominator, it's basically a free answer. Negative infinity to infinity. Free answer. Yeah. I love to put those kind of things on quizzes and tests and things because sometimes people don't take the free answer. They can't remember. They panic. And they actually try to solve the problem. All right, this is one of those problems where if you try to solve the problem, you missed the whole point. Yeah, the point is there is no problem here. Move along. Move along. You're not going to find it here. Why don't I just keep the instructions up here? I don't have to write them again. Is there a problem here? Do we have a problem? No, we have no problem. Look, this is not a square root. This is a cube root. No problem. All right. The rule says square roots. Yeah, that's how we get imaginary numbers. Imaginary numbers didn't come from cube roots. They came from square roots. There's also no denominator. Yeah. So again, no problem. Smile. Take your free answer and move along. On the homework, I put probably like 5 of these. And they're all scattered through the homework, so you never know when one's going to pop up. But keep your eyes open. You notice that there's no problem. No, this is an old saying of mine. Not every problem is a problem. Now, some problems are just gifts. Just take it. Free answer. Take your points. You know what's funny about it? Is a problem that's not a problem is worth just as many points as an actual problem. So there you go. You get your full credit, full amount of points as if you actually did something, but you didn't do anything. You just read the directions and remembered the material, and you get the same amount of points. How do you like them apples? All right, one more of these and we'll move on to another exciting adventure in this domain world that we're in. Find the domain in interval notation. That's the most common notation. If you're not sure, then that's always a good guess, a good bet. So what are we at now? We're at, I don't know, square root of 15 minus 12x. Sometimes we put the 2 here to indicate that it's a square root. So this little 2 right there is often invisible. It's called the index. And it's understood in mathematics that if you do not see an index, that is an automatic 2. I sometimes put it, I sometimes don't. You have to be flexible. You don't want to insist upon yourself. But you might notice on your iPhone or on whatever type of smartphone you have, if you do the cell phone calculator, they actually still put the 2 on there as if it were the 1980s. What's funny is we didn't even have smartphones in the 1980s, but back in the 1980s, pretty much everybody wrote the 2 back then. I saw it in every math class I was ever in. Okay, so remember, this is the rule of square roots. So the rule is take the radicand and set it to be greater than or equal to. Don't forget the or equal to part. Greater than or equal to 0. And you're going to solve this for x. Now the cool thing about these equations is you already know how to solve them. Basically, in Chapter 2, we learned how to solve every type of equation until we get to Chapter 6. So everything has already been covered. This is exactly the same as an equation. Just bring it down just like an equal sign and just get the x by itself. Now, I'm not sure if you remember from intermediate or beginning algebra, there is one special rule of inequalities. If you divide by a negative, you have to reverse the inequality. So you have to reverse this inequality if you divide by a negative. In the last time that I did this type of problem, I did not divide by a negative, and so I did not reverse the inequality. So keep that in your mind. That's basic algebra or sometimes intermediate algebra, depending on where you learned it. All right. A negative divided by a negative is a positive. And you can reduce this. 15 divided by 3 is 5, and 12 divided by 3 is 4. So you're going to get x is less than 5/4. Okay, the interval notation, less than, remember left infinity. This is less than. And then including 5/4. So you're going to put a square bracket to say that you're including the 5/4. And so that is your domain in interval notation. I guess you could say 1.25 if you really wanted to use a decimal. I'm not sure. To be safe, unless it says decimal on the homework, just don't do it. It's not worth it. It's not worth the frustration of thinking that you got it wrong when you should have just left it as 5/4. Although it still is 1 1/4, right? 1.25. So. All right, so that's it for the domain rules, at least for the introduction to the domain rules. They get worse, all right? So if you want to go take a breather right now, would probably be a good time because they're going to get a lot worse. I might as well have just made this the instruction for the whole lesson, but there are a few problems that do not use that instruction, so I have to be very careful. All right, you ready for the next one? A couple things I might mention is that functions are not always called f. really is no rule for what you're going to call a function. You can call a function anything you want to call it. Okay. Now, I usually just take the name that it's given, but I mean f, g, h, k, these are all common names for functions. All right, so you see what we have here? This is sometimes called a hybrid. Yeah, it's a hybrid of two different types of functions. Yeah, it's part radical, part rational. It's a rational. So we have to apply both rules. All right. So rule number 2 says that the radicand must be greater than or equal to 0. And rule number 3 says that the denominator must not be equal to 0. So we are dissecting this into its two independent parts. We have rule 2 and rule 3. Remember, rule number 1 doesn't apply because if rule 2 or 3 apply, then remember what rule number 1 was. Rule number 1 was the absence of rules 2 and 3. So obviously, this is only rules 2 and 3. So let's go ahead and solve these. Now, on this example, I made the equation or the function look complicated, but watch how easy the answers are. I often do that. I want you to see that not every problem has to be complicated. Even problems that look complicated are actually very simple. If you learn that lesson, then you will pass this class, because there is not one single complicated problem in this whole entire class. They might look complicated, but that's just your eyes. That's the illusion. Don't believe it. Yeah, so split these up, make them both equal 0. You know what? I'm not doing this. You guys all know how to add. So x plus 10, obviously it's negative 10. X minus 1, obviously that's 1. I don't need to treat you like you're in 5th grade, right? So you know how to add, you know how to subtract. So there you go. So what do we have? X is greater than negative 12, and X is not negative 10, and X is not 1. Yeah? You want to draw a picture of that? Sometimes it helps to see what the hell you're talking about. Just draw a picture. So way over here is negative 12. Over here is negative 10. You don't have to be very precise. Here's 0 and here's 1, okay? So what are we saying? X is greater than or equal to negative 12. So solid dot, because it is touching negative 12. It is not touching negative 10. And it is not touching 1. But remember, domain means every single possible number. So all of these numbers and all of these numbers, you can just erase the 0. The 0 really doesn't matter. Why did I have it? I just wanted to know where the negatives stopped and the positives began. So if you like to put 0 as a reference, you can certainly do that. But I don't want to see it in the final answer. So I'm actually going to erase it. And then everything greater than 1 all the way to infinity. So your domain is square bracket, including negative 12, all the way to negative 10, not including negative 10, union, negative 10, all the way to 1, not including 1, union, not including 1, all the way to infinity. Infinity and negative infinity, if they appear in your answer, they're always in parentheses because you can never actually include infinity. It's too far away. It's an idea that you'll never see, except symbolically. Yeah? Hey, welcome to infinity. We've been waiting for you. Okay, so that's your answer. Interval notation. Okay, I think only one more hybrid. Example 8. And then we're going to have to go to the graphing. We're going to have to go to the graphing and range. It's been almost an hour and I still haven't talked about range yet. It's because the domain is so much more important. All right, one more example. Find the domain, and of course, you know what it's going to be, interval notation. So what do we got? Let's see, h of x. That's another name for a function. H of x is negative 6x squared plus 7x over the square root of 8x minus 20. All right. So what rule is this? Well, the first thing you might notice is look at the top. The numerator has no square roots. I like to put squares to see if I can trick you. I'm not really trying to trick you. I'm trying to educate you. That is not a square root, okay? So you can ignore that. All right? It does not apply to any of the rules. Ignore it. We're going to apply rule number 1. Excuse me, this is rule number 1. So rule number 1. This is rule number 2. All right, rule number 1 says if there are no square roots and there are no variables in the denominator, you can ignore it. So that's it. Rule number 2, you're going to take the radicand and you're going to say that it is greater than or equal to 0. Yeah, but it's also in the denominator. Right? If it's in the denominator, it's rule number 3. So rule number 3 says what? The denominator cannot be equal to 0. So I'm applying both of these rules at the same time. Yeah. Now, they just so happen to be the same function. So last time I was applying rule number 1 to one and rule number 2 to the other one, or rule number 3 to the last one, or whatever it was. These are the same exact equation. I'm just applying both rules to it. Yeah. So it's sort of double jeopardy here. All right. Now, here's what you can do. If you really want to solve 2 problems, go right ahead. You certainly can. But since these are the same problem, why don't we just solve it one time and then apply the answer to both? Pretty good idea, right? If this is greater than or equal to, and this is not equal to, why don't we just apply them both and say it's greater than? Think about that. Greater than or equal to and not equal to. Well, that just means greater than. I hope I don't need to explain that one again. So we're going to add 20 to both sides. Divide by 8. Should I reverse it? I can hear it through the internet. No, don't reverse it. Why not? Because I'm not dividing by a negative, so leave it alone. Sometimes when people hear that reverse rule, that's all they remember is to reverse, and then they start reversing every single time I do it. But it's only if you're dividing by a negative. That's the key. So 20 divided by 8, let's see, we can reduce that. That'll be what? 5 halves. Yeah. 4 goes into 25 5 times. 4 goes into 8 2 times. And I think I've already overstated that. So the domain, not including 5 halves, all the way to infinity. Yeah, greater than, great means right. Less means left. You know why? Because right-handed people made all the rules. So whenever you say greater, you mean right. Whenever you say lesser, you mean left. All right, that's it for the domain rules. Practice, practice, practice. You'll get good at it. Take the free answers. I sprinkled a few free answers in there. Those are the ones that are just automatically negative infinity to infinity. Now we're going to move on and talk about the graphs and the range. There really are no range rules. Yeah. There just are none. If there were range rules, then I would be now giving you a whole bunch of rules for range. In order to determine the range, you must first have the graph, or you must have a very good imagination where you can imagine the graph. But the range is like the word implies. It is the image. That's where we get the word range from. Yeah. The domain is the inputs, and then those inputs produce the image called the range. And without the graph, it's almost impossible to find out what the range is. So in the next few examples, I'm going to provide you with the graphs. But keep in mind that we're still in our Chapter 3 honeymoon phase, where I'm basically giving you all the graphs. That won't last for much longer. At some point, you will have to draw these graphs yourself. So given the graph, you can say, thanks, Dr. Jordan, for giving me the graph. Find the domain and range. All right. So let's see. I should probably use the board. I typically label X and Y, but if I don't label them, you are to assume the obvious. Horizontal is X, vertical is Y. Okay. On this board, each tick mark or each unit represents 1. That's typically the way I do it, unless there's some reason why that doesn't work. I'll change my scale a little bit. Okay, so each unit represents 1. So this is -4. This is +5. This is +4. And this is -3. You might recognize the shape of this. This is a parabola. It's what we call a truncated or a restricted parabola. It means that the parabola does not go on forever. It's been truncated. Truncated means cut. So it's sort of like you've trimmed your parabola. All right. An open hole means not including. Yeah. Or not touching. Yeah. Okay. And a closed means including or touching. I got a really bad joke. It's sort of counterintuitive, right? Closed means you can go in. Yeah, you can go in there. You can touch it. Yeah, you can go inside because it's closed. Open means go away. You can't come in. You can't touch. Closed. Yeah. So in math land, when you put a sign on the door that says closed, come on in. We're closed. Welcome. We're closed. When you put the sign that says open, open means go away. Don't touch. You cannot come in. We're open. Yeah. Some people get confused with the fact that that's bass-ackwards, right? Open, go away. Closed, come on in. Yeah. That's math. That's math for you. All right, so remember, domain is all possible inputs or all possible x's. The smallest possible x is -3. -3 is open. Open, not including -3. Yeah. All the way to the largest possible x, which is 5. 5 is closed. See, you can actually touch 5. So that's your domain. Some people go so far as to actually shade it on the number line. I'll do it once, I guess, if you really want to see it. So that's domain. Yeah, it's not required. It's just if you like to do this, you certainly can. I won't be grading any of that. Okay, that's just scratch work if you really want to do it. All right. So that's your domain, the x values. Range. Remember, all possible. Range is all possible y's. All right, that's your range. All possible y's. So the smallest possible y is -4, and it's open. You're not actually touching -4. The highest possible is +4. If you don't see a dot, assume it's closed. That's just a basic assumption throughout the rest of this course. If you see a graph and you don't actually see a solid dot, then that means it's closed. All right. And there you go. So again, you have open and closed. So that is your domain and range using interval notation. Again, some people like to do this in basic algebra. I think, if I had you in my classroom, I might make you do this, and I'd grade your actual shading on the number line. I'm not grading your number line shading. That's beneath the scope of this course. So, but I mean, if you still like it that way, you learned it that way, you want to do that for your scratch work, that's certainly fine. All right, so that's range. And this is domain. Let's put DOM for domain. Very quickly, before I do the next problem, this problem's basically done, but before I erase all of this stuff, I just want to show you the other notation. The other notation is set notation. If I have enough room for it here, the domain and set notation is the set of all x such that x is greater than -3 and less than 5 or equal to 5. Less than or equal to 5. So that is your domain translated into set notation. And if I did it with the domain, I should probably do it with the range as well. The range is the set of all y such that y is greater than -4 and less than or equal to +4. So that would be your domain and range written in, oh, I almost screwed up. Domain is x, range is y. Whew, that almost cost me an extra credit point. Okay. Or that almost earned one of you an extra credit point. Not today. All right, so that is how to find domain and range from a graph. Let's do another one. right. Stay focused. I'm talking to the camera. Stay focused. Pardon my line is not very straight, but it's not going to affect the answer, so I'm not going to redraw it and make you watch me draw a line that's probably won't be much straighter than that one. So. All right, so given the graph, find the domain and the range. Again, assume that each mark is 1 unit. That's going to be always true in this class unless I specify otherwise, which will be very rarely. Only in dire circumstances would I ever change my scale. Mostly if I just can't fit on the board that I have. So here we go. Find the domain and range. Again, this is what we call a truncated or restricted line segment, or line you could call it, but it's been restricted. We have an open, we have a closed again. I guess I'm being kind of predictable with the open. Maybe they could be reversed. You know, the closed could be on this side and the open could be on that side, but I wasn't that creative today. I just kept it the same as the last example. So I'm not going to do another one with them switched. You can do it yourself if you want to see it switched. So this is 1, 2, 3, 4, 5, -6. All that matters is the least and the greatest. So this is 1, 2, 3. And you do not have to list every number in between. In fact, I don't want you to list every number in between, just the least and the greatest. The least here, the lowest bound is -2, and the upper bound is 1, 2, 3, 4, 5. Okay. Sometimes those numbers are already listed for you. If they are, then only circle or highlight the ones that matter. I often get students that remember 3.1 where they went, -6, -5, -4. I don't want to see every single number. All right. So domain. All possible x's. -6, comma, 3. -6 is an open circle. 3 is closed. Range, -2 is closed. See, -2 is closed, and 5 is open. And that's it. I mean, it's really not a math problem. It's a reading problem. You just read the graph and write down the answer. This would be the interval notation. The other notation would be the set notation. So you'd say domain, the set of all x, such that x is greater than -6 and less than or equal to 3. All right, and then range. Be careful with the variable. I often screw these up because I just put the wrong variable. So it's y, such that y is greater than or equal to -2 and less than 5. And that's it. That's your domain and range. All right. Now, most of the graphs that we do in this class are not truncated. Most of the graphs, well, now we got one more truncated. One more truncated. One more, and then we'll do the non-truncated. Or non-restricted is another way to say it. So one more of these. Given the graph, find the domain and range. One more. Let's see if I can just use this without having to redo the whole thing. That would be nice. All right, so let's see. I know. All right, so one more of these guys. Let's see. I'm coming. All right, so here's the graph. All right, it's not the prettiest thing, but it will do the job. I think for me to try to make it look nicer would just take more time, and it might not even help. So let's just leave it the way it is. Okay. All right, so let's fix that one. That one was kind of sloppy. There we go. That's a little bit better. Man, the more I try to make it better, the worse it gets, isn't it? Isn't that the story? Okay, so where are we at here now? We want the domain and the range. This one has an arrow, okay? And so if you see an arrow, you are to assume that the graph continues forever in that direction. Whatever that direction happens to be, in this case it's up. Yeah, it's up and left. All right, so this is left and up. So this arrow is continuing in that direction forever. So when I do the domain, we are assuming that this graph is going to go left forever. It's forever left. So the symbol for forever left is negative infinity. It's going left forever. Okay. And then the symbol for going to the right would be positive infinity, but it is not going forever right. It is stopping at 3. There is no arrow on this side. So it's stopping at 3, and 3 is an open circle. The range. All right. Now the range we do from the bottom up. All right. So what's the bottom? -1, -2, -3. Looks like -4. That's why I wanted to clarify that circle to make sure. It's also open, -4, and it looks like it goes to 3, yeah, because this point right here is at 3, right? 1, 2, 3, but it's actually going forever up. Yeah, so the range is going to go forever in that direction. So the range is 4, infinity. For this one, I'm just going to give you interval notation only. If you want the set notation, I'll just do it FYI. It's not on the homework, but some people like to know it anyway. You'd say x is less than 3, and then that'd be DOM, and then range would be y is greater than -4. So these are sometimes called one-sided inequalities. It means that the variable is only on one side of the inequality. It's not on both sides. All right, we've come to the end. I've got a couple more examples of graphs that have no truncations, no endpoints. Graphs from your catalog of functions. Example 12. Find the domain and range using interval notation. These are the most common. So as we move through the rest of chapter 3, these are the types of graphs that you will see most frequently. Most graphs do not have endpoints, but some do. And some don't. So you just have to So here's an example of one of the graphs from our catalog of functions. Although it's not drawn perfectly, it's just a rough sketch of a quadratic graph. Again, assume that every mark is 1, 2, 3, 4. That's 4 units. That's 1, 1, 2, 3, 4, 5, 6, so on and so forth. And then assume that these go on forever in this direction. Actually, it's going to be like this. In other words, it's going to go forever down. Yeah. And forever left, by the way. So this graph will go left forever and down forever. Yeah. This graph, this side of the graph, will go right forever and down forever. I don't have to say down again. However, it will not go up forever. It will stop right here. This is the highest point. Yeah, so that's our highest point. So our graph goes domain left forever, yeah, right forever. Yeah. So all of these numbers in the middle are irrelevant. Those are all possibilities, but the domain is forever left, forever right. That's your domain. Done. It's essentially a free answer. And then range is not free. You have to look very carefully at the graph. Look at the y value for range. It's going down forever, but the highest point is 4, and you assume it's closed. If you don't see something indicating it's open, then that closed is the automatic assumption. Okay. So what we're going to do next is I'm going to end the video now, but I want you to go through all of the, it's what I call a DIY. Go through the whole catalog. Of functions. You already have all the graphs from 3.1, and find the domain and the range of each function. All right, and you can do it simply by looking at the graph from the catalog of functions. All right, DIY stands for do it yourself. Here, I'll get you started. I'll do one for you, okay? So from the catalog of functions, we have absolute value. Okay? Don't look at the table of values. That's not considered the domain and range anymore. That was just the primitive to get the ball rolling. Look at the highest or the lowest point. So the domain for the absolute value would be negative infinity to positive infinity. Yeah. Now look very carefully at the range. Yeah. The range would be 0, assume this is closed. Yeah, it's touching there, all the way to infinity. So that's what I mean. Go through the entire catalog. You don't even have to do the problems over again. Just go through all of the ones that I gave you in 3.1 and add in their domains and ranges. There are 7 more. Okay. If you have any trouble finding all the domains and ranges, you can email me. You can come to my Zoom office hours, which start at 11 o'clock. I don't know what time you're watching this, but on Tuesdays and Wednesdays. All right. Until then, see you on the internet.